Welcome to a crucial new module on Pandas. If NumPy is the foundation of scientific computing in Python, Pandas is the universal tool for data manipulation and analysis. It provides high-performance, easy-to-use data structures and data analysis tools, making it the industry standard for handling tabular data. 1. What is Pandas? Pandas is an open-source Python library providing high-performance, easy-to-use data structures and data analysis tools. It is built on top of the NumPy package, meaning that NumPy's fast array operations are integrated into Pandas. Pandas is ideal for working with relational or labeled data, similar to data found in spreadsheet programs or SQL tables. Before importing, we must install Pandas. You open your terminal and run this command. 2. The import convention. Just like NumPy, Pandas has a standard import convention. You should always import it as import pandas as PD. This convention is universally used and ensures your code is recognizable and consistent within the Python data community. 3. Core data structures. Pandas introduces two primary data structures. First is the series. Think of a series as a single column of data, similar to a 1D NumPy array, but with labels called an index. Second is the DataFrame. This is the most common structure, representing data in rows and columns, like a table or spreadsheet. A DataFrame is essentially a collection of series objects that share the same index. We will focus heavily on both of these in the coming lectures. To summarize, Pandas is the key to working with real-world data. Our next lecture 36.02 series. See you there. Welcome back. In the last lecture, we introduced the series and the data frame. Today, we focus entirely on the series. Understanding the series is the foundational step because a data frame is, at its core, a collection of series objects aligned along a shared index. The series is the one-dimensional workhorse of Pandas. 1. Definition of a series. A Pandas series is a one-dimensional array-like object capable of holding any data type, such as integers, strings, floating point numbers, or Python objects. It consists of two main parts: the data, which is essentially a NumPy array, and the associated index, which labels each element. 2. Data versus index. When we create a series from a standard Python list, Pandas automatically assigns a default numeric index starting from 0, just like a list index. In the output, the right-hand column shows the actual data values, and the left-hand column shows the index labels, which are 0, 1, 2, and 3. The data type, or D type, is shown at the bottom. 3. Series attributes. You can access the two main components using attributes. The values attribute extracts the data as a pure NumPy array, stripping away the index. The index attribute returns the index object itself. This is particularly useful for verifying the labels. Finally, the D-type attribute tells you the Pandas data type, mirroring the NumPy D-type. To summarize, the index is what separates a series from a simple NumPy array. Our next lecture 36.03, Create Project. See you there. Welcome back. Before we dive into creating and manipulating Pandas series objects, let's take a quick moment to set up our project files. Having a clean and organized structure will make it easy to follow the coding examples throughout this module. 1. Creating the demo files. We will create two main files for this module. The first is series_demo.py. This file will contain all our examples and code related to the one-dimensional series data structure. The second is DataFrame_demo.py. We will use this file for all our examples involving the two-dimensional DataFrame structure. 2. Initial imports. In both of these files, add the standard import lines. We need import pandas as PD, and since pandas relies heavily on NumPy, we also include import numpy as NP. This ensures all the necessary libraries are ready to go when we start coding. To summarize, your environment is set up. Our next lecture 36.04, Create and Use Series. See you there. Welcome back. In this lecture, we will get hands-on with the Pandas series object. We'll demonstrate how to create a series from various standard Python structures and explore how to access individual elements using the default integer index. 1. Creating series from Python objects. There is a way to create a series is by passing a data structure into the pd.series constructor. When passed a Python list or a NumPy array, Pandas uses the data and automatically assigns a default numeric index, starting at 0. Notice how the d-type is inferred from the input data. Two. Series from a scalar value. You can also create a series from a single scalar value. However, you must explicitly provide an index to tell Pandas how many times to repeat that value. Here, we pass the scalar 5 and an index list of length 5, resulting in a series where all 5 values are equal to 5. 3. Accessing elements by index. You access elements in a series using the square bracket notation, similar to accessing items in a list. When using the default index, you pass the numeric position. For the series with values 10, 20, 30, passing 0 returns 10, and passing 2 returns 30. To summarize, creating a series is straightforward. Next, we will explore the real benefit of the series, using custom, meaningful index labels. Our next lecture 36.05, Use Custom Indices. See you there. Welcome back. The true power of a Pandas series, beyond a simple NumPy array, is its ability to use meaningful, custom index labels. In this lecture, we will learn how to assign non-numeric labels to our data, making data retrieval much more intuitive. 1. Creating series with custom indices. To assign custom labels, you pass a list of labels to the index argument in the pd.series constructor. These labels can be strings, dates, or other meaningful identifiers. This allows us to retrieve data using a label that directly describes the information, like a dictionary key. 2. Accessing elements by label index. Once custom indices are set, you can retrieve elements by passing the label string directly in the square brackets. This is much more robust than relying on integer positions, as the data remains labeled even after sorting or restructuring. You can also retrieve multiple items by passing a list of labels. Three, accessing elements by position index. Even with custom labels, the series retains its underlying zero-based integer positioning. You can still access elements using the numerical index, and this method is necessary for slicing by position. However, it is generally better practice to use the label index for accessing specific labeled data points. To summarize, custom indices turn numerical arrays into self-describing data objects. Our next lecture 36.06, Series of Strings. See you there. Welcome back. While we've primarily worked with numerical data so far, Pandas truly shines when working with real-world, often messy, string data. This lecture explores how to create and, more importantly, efficiently manipulate series composed of strings using Pandas' vectorized string methods. 1. Creating a series of strings. Just like numbers, you create a series of strings by passing a list of string values. The D-type is typically object or string, depending on your Pandas version. Notice that in real-world data, strings often contain unwanted leading or trailing whitespace or inconsistent capitalization. This is where vectorized methods become essential. 2. Vectorized string methods. Python string methods like lower or strip normally operate only on a single string. Pandas introduces the str accessor, which allows you to apply these methods to every single string element in the series, without writing an explicit loop. Here we use .str.strip to remove whitespace, and then chain.str.lower to standardize the capitalization. This element-wise application is fast and clean. 3. Conditional string operations. You can also perform checks on the strings. For example, .str. contains checks if a substring is present in each element and returns a Boolean mask. We can then use this mask, which we learned about in the NumberPy module, to filter the original series and extract only the cities containing the letter O. To summarize, the .str accessor is your key tool for text processing in Pandas. Our next lecture 36.07, Describe. See you there. Welcome back. A crucial first step in any data analysis project is getting a quick overview of your data's statistical properties. Pandas provides a powerful single method for this, the .describe method. This lecture will show you how to use .describe to generate descriptive statistics for numerical data in a series, and what happens when you use it on string data. 1. .describe on numerical data. When applied to a series containing numerical data, the .describe method returns a new series containing 8 key statistical measures. These include the count of non-null values, the mean, the standard deviation, the minimum and maximum values, and the quartile values, the 25th, 50th, and 75th percentiles. This provides an excellent snapshot of the data's distribution and potential outliers. 2. .describe on object or string data. When applied to non-numerical data like strings, .describe returns a different set of summary statistics relevant to categorical data. These typically include the count, the unique count, the top or most frequent value, and its frequency. This is useful for understanding the diversity and distribution of categories within your dataset. 3. Calculating individual statistics. While .describe is great for a quick overview, you can also access any of the individual statistics directly using dedicated methods on the series object, such as .mean, .median, .max, and .min. These methods return a single scalar value. To summarize, .describe is your go-to function for initial data profiling. Now that we understand the series, we are going to move on to the primary data structure of Pandas, the DataFrame. Our next lecture 36.08, DataFrame. See you there. Welcome back. We are now moving on to the most important structure in Pandas, the DataFrame. This is the primary data structure used for all tabular data, representing data in rows and columns, just like a spreadsheet or a SQL table. Understanding its components is key to mastering data analysis in Python. One. Definition of a data frame. A Pandas data frame is a two-dimensional, size-mutable, and potentially heterogeneous tabular data structure. Think of it as a dictionary of series objects, where the keys are the column names. Each column is a series, and all series share the same index, ensuring that the data across rows is aligned. 2. Two indices, rows and columns. Unlike a series which has one index, a data frame has two. The row index, often just called the index, labels each record or observation, similar to the series index. The column index, or column labels, names each variable or feature, usually referred to simply as the columns. You can access these labels directly. 3. Data frame structural attributes. Like NumPy arrays and series, data frames have useful attributes. The shape attribute returns a tuple of rows, columns. The ndim attribute is always 2 for a data frame. Unlike the series, the dtypes attribute returns a series listing the data type for each column, reflecting the data frame's heterogeneous nature. To summarize, the data frame is the cornerstone of data manipulation in Python. Our next lecture 36.09, Create Data Frame. See you there. Welcome back. In the last lecture, we learned that a data frame is a table with labeled rows and columns. In this lecture, we'll cover the most common way to construct a data frame, using a Python dictionary where keys become column names and values become the data within those columns. 1. Creating data frame from a dictionary of lists. This is the simplest and most intuitive method. You organize your data into a Python dictionary where each key is a column name, and the corresponding value is a list of data for that column. When passed to the pd.dataframe constructor, Pandas creates columns from the keys and assigns a default numeric index to the rows. Two. Specifying column order. By default, Pandas often maintains the insertion order of the dictionary keys, but for guaranteed consistency, or to reorder the columns, you can pass an explicit list of column names to the columns argument. Three, assigning custom row indices. Just like with the series, you can assign custom labels to the rows by using the index argument. Here, we use a 1, 2, 3 index instead of the default 0, 1, 2, which can be useful for human-readable indexing. To summarize, data frames are highly flexible upon creation. Our next lecture 36.10, Access Columns and Rows. See you there. Welcome back. Having created a data frame, the next critical step is learning how to efficiently retrieve specific data. In this lecture, we cover the primary methods for accessing columns, which are returned as series objects, and accessing rows, which requires the use of special accessors. 1. Accessing columns using bracket notation. Accessing columns is similar to accessing values in a Python dictionary. You pass the column name as a string inside square brackets. The result of extracting a single column is always a Pandas series. You can verify this by checking the type. 2. Accessing columns using dot notation. As a shortcut, you can often use dot notation, like df.tem, provided the column name contains no spaces or special characters and doesn't conflict with built-in data frame methods. While convenient, the bracket notation is generally safer and more flexible. 3. Accessing rows by label. To access rows, you must use one of the specialized row accessors. The first is .lock, which stands for location. It is strictly label-based. You pass the custom row label inside the square brackets after .lock. The result is a Pandas series, where the original column names become the new series index labels. 4. Accessing rows by position. The second accessor is .iloc, which stands for integer location. It is strictly position-based, meaning you use the zero-based integer index, regardless of whether the row has custom labels. This is necessary if you need to access a row based on its physical order in the data frame. To summarize, always use .lock or .iloc for rows, and square brackets for columns. Our next lecture 36.11, Use Slicing and Lists. See you there. Welcome back. In the previous lecture, we accessed single columns and rows. Now, we expand those concepts to retrieve subsets of our data, multiple columns and multiple rows at once. Mastering slicing and using lists within the accessors is essential for extracting specific data blocks. 1. Selecting multiple columns. To select more than one column, you pass a list of column names inside the square brackets. Note that this requires double brackets. The outer brackets are for indexing, and the inner brackets define the list of column names. Crucially, selecting multiple columns returns a new data frame, not a series. 2. Slicing rows with .lock. When slicing rows using .lock and custom labels, the stop label is inclusive. This means the row with label R3 is included in the result, unlike standard Python slicing. We specify the start row and the end row, separated by a colon. Three, slicing rows with .ilock. When slicing with .ilock, we use the zero-based integer positions, and the stop index is exclusive, behaving exactly like standard Python list slicing. Here, 1:3 selects rows at position 1 and position 2. To summarize, mastering the inclusive nature of .lock slicing and the exclusive nature of .ilock slicing is crucial. Our next lecture 36.12, Getting a Subset. See you there. Welcome back. We have learned how to select columns and how to select rows. In real-world analysis, you often need to select a specific rectangular subset of your data, a block of several rows and several columns. This is achieved by combining the row and column selection methods using the .lock or .ilock accessors. 1. Setup. Custom Index DataFrame. We first create a small 3x4 data frame with custom labels for both rows, R1, R2, R3, and columns, C1 through C4. This allows us to clearly demonstrate the label-based and position-based access. Two, selecting subsets with .lock. To select a rectangular subset, we use the syntax df.lock, row selector, column selector. The row and column selectors are separated by a comma. We can use slicing for the rows, say R2 to R3, and a list for the columns C1 and C3. Remember, .lock slicing is inclusive, so R3 is included. Three, selecting subsets with .ilock. Similarly, .ilock uses integer positions. We can use a list for the rows 0 and 2 and slicing for the columns 1:4. Remember, .ilock slicing is exclusive, so position 4 is not included. This syntax is extremely powerful for extracting any part of your data table. To summarize, the combination of row and column selectors allows precise subsetting. Our next lecture 36.13, Query for Data. See you there. Welcome back. While structural indexing like .lock is useful, the true power of data analysis lies in conditional selection. Asking your data questions like, show me all records where the value is greater than a certain threshold. This is achieved using Boolean masking, which relies on the concepts we learned in the NumberPy module. 1. Creating the data and a single condition. To filter data, we first create a Boolean series or mask. We access the price column and apply a condition, asking if the price is greater than 200. The result is a series of true and false values, corresponding row by row to whether the condition was met. This mask is the key to conditional selection. 2. Filtering the data frame. To filter the data frame, you pass the Boolean mask directly inside the square brackets of the data frame. Pandas automatically selects only the rows where the mask is true. This operation extracts all columns but only the rows that satisfy the condition. Three, combining multiple conditions. For complex queries, you can combine multiple conditions using the bitwise operators. Use the ampersand sign, for and the pipe sign, for or. It is essential to wrap each individual condition in parentheses to ensure correct operator precedence. To summarize, Boolean masking is the primary way to perform database-style queries on your DataFrame. Our next lecture 36.14. Pick a cell. See you there. Welcome back. We've covered how to access entire columns, rows, and rectangular subsets. The final and arguably most precise access method is picking out or modifying a single individual cell value within the data frame. For this, Pandas provides two highly optimized accessors, .at and .iat. 1. Setup, sample data frame. We will work with a simple data frame that has custom row indices R1, R2, R3, and column names A and B. 2. Accessing a single cell by label using .at. The .at accessor is designed for label-based lookup of a single value. Its syntax is df.at, row label, column label. This method is significantly faster than using .lock for single-value lookups. You can also use .at to assign a new value to the cell, as we do here by changing the value at R2, B to 999. Three, accessing a single cell by position using .iat. Similarly, the .iat accessor is optimized for integer-based, positional lookups. Its syntax is df.iat, row position, column position. This is the fastest way to access a single cell by its physical coordinates. We can also use it to set a new value, like changing the cell at position 1, 0 to 888. To summarize, .at and .iat are your preferred methods for working with individual cell values. Our next lecture 36.15, Describing and Transposing. See you there. Welcome back. In this lecture, we look at two utility functions that are incredibly useful for initial data exploration. First, reapplying the .describe method to the data frame, and second, transposing the data frame to quickly swap rows and columns. 1. .describe on a data frame. When you apply .describe to a data frame, it automatically computes the descriptive statistics only for the numerical columns, treating each numerical column as an independent series. The resulting data frame provides a clean table of statistics, making it easy to compare the central tendency and spread across different variables. 2. Transposing the data frame. Transposition is a mathematical operation where rows become columns and columns become rows. In Pandas, this is done by simply accessing the .t attribute. This is useful when you have many columns and few rows, and you want the data to be more readable. For example, if you describe a data frame and the result is too wide, transposing it can make the statistics much easier to view vertically. Three, analyzing transposed statistics. Combining these two concepts is a common technique. By calling df.describe.t, we first calculate the statistics and then transpose the resulting table. This is often the preferred way to view descriptive statistics, as it lists the column names vertically and the statistics horizontally. To summarize, .describe and transposition are great tools for initial data inspection. Our next lecture 36.16, Sorting. See you there. Welcome back. Sorting data is a fundamental step in almost any analysis, whether you want to quickly find the top performers or organize time series data chronologically. In Pandas, we have two primary methods for sorting, one for sorting by the values within columns, and one for sorting by the index labels. 1. Setup. Sample data frame. We start with a data frame containing city data, with columns for city name, population in millions, and an existing rank. Notice the current row order is arbitrary, not sorted by any meaningful column. 2. Sorting by column values. The df.sortValues method is a way to sort. You must pass the column name to the by argument. To change from the default ascending order to descending, you set ascending to false. Notice that the entire row moves when sorted, but the original index values 0 through 3 are retained next to the correct data. Three. Sorting by multiple columns. You can specify multiple sort columns by passing a list to the by argument. Pandas sorts by the first column, and then uses the second column as a tiebreaker, and so on. 4. Sorting by index labels. If you want to sort the rows based on the row labels rather than column values, you use the df.sortIndex method. This method has no by argument. You can still control the order using the ascending argument, which defaults to true. To summarize, sorting is essential for data organization. Our next lecture 36.17, Working with CSV Files. See you there. Welcome to the final segment of our Pandas module, where we shift our focus from creating data frames manually to working with real-world data files. There is a format for sharing tabular data is the comma-separated values, or CSV, file. Understanding how to interact with CSV files is a requirement for any data scientist. 1. What is a CSV file? A CSV file is a plain text file that stores tabular data. Each line in the file represents a data record, and each field, or column value, in the record is separated by a comma or another delimiter. This format is simple, universally compatible with most data tools, and highly efficient for storing large datasets. 2. Pandas and File I/O. Pandas is the bridge between your text-based CSV files and the powerful DataFrame object. It provides highly optimized functions for reading data from external files into a data frame and for writing a data frame back out to an external file. 3. The core CSV functions. we will focus on two main functions. To bring data in, we use pd.read_CSV. This function reads the data and returns a DataFrame object. To export data, we use the DataFrame method, .to_CSV. This method writes the DataFrame content to a specified file path. To summarize, CSV files are crucial for data exchange. Our next lecture 36.18. Read data. See you there. Welcome back. In this lecture, we focus on the function for importing data, reading a CSV file into a data frame using the powerful pd.read_CSV function. We will cover the basic usage and two essential arguments for correctly structuring your data upon import. 1. Basic CSV data import. The simplest usage of pd.read_CSV only requires passing the file path. By default, Pandas is optimized for standard CSV files, meaning it assumes commas separate the values, and the first line contains the column headers. The result is always a data frame, and we use the .head method to quickly inspect the first 5 rows. Two. Handling non-standard CSV delimiters. Although we call them CSV files, they don't always use a comma. If your file uses a different character, like a semicolon or a pipe, to separate the values, you must specify it using the sep argument. Failing to do so will result in a data frame with only one column containing all the data lumped together. Three. Specifying the index column. If your data file contains a column that serves as a unique identifier and should be used as the custom row index for cleaner access, you use the index_call argument. You can pass either the column's name, such as ID, or its zero-based position. This moves the chosen column from the data area to the row label area. To summarize, .read_CSV is essential for getting data into Pandas. Our next lecture 36.19. Write data. See you there. Welcome to the final lecture in our Pandas module. After all the analysis and data manipulation, the last crucial step is saving your work. In this lecture, we cover how to use the DataFrame method, .to_CSV, to export your clean, processed data frame back into a CSV file, and how to prevent unwanted elements from being written. 1. Basic data export. To save your data frame, you simply call the .to_CSV method on the DataFrame object and pass the desired file name as an argument. By default, this method includes the column headers on the first line and, importantly, writes the row index as an extra unlabeled column. Two. Omitting the row index. Since the automatically generated row index is often unnecessary for the recipient, it is common practice to omit it. You do this by setting the index argument to false. 3. Omitting column headers. In some specific cases, like appending data to an existing file, you may not want to include the column names. To suppress the column names, you set the header argument to false. Here we also combine it with index equals false to produce a file containing only the raw data. To summarize, the .to_CSV method is essential for exporting your final data product. This concludes our section on the Pandas library. You now have the skills to create, manipulate, and analyze tabular data. Our next section is Matplotlib, starting with Lecture 37.01, Introduction. See you there.